Yeah, so in this talk, in this webinar, I will be telling you about my PhD research I've done in Groningen as well as in Zeeland, combined with the University of Groningen and University of Zeeland, as well as the Helmholtz Institute of Pharmaceutical Research in Zeeland. And the topic of my PhD research was finding new applications of dynamic combinatorial chemistry to medicinal chemistry. And as I mentioned, I started in Groningen, and our research group then moved from Groningen to Saarbrücken. And I just joined. I wanted to join and want to see Saarbrücken as well and find this nice co-tutel agreement. So having this double doctorate was of interest of me as well. But maybe you can see from here, there's quite a distance, and we had to move and emigrate, so to say. So from the Netherlands to Germany. But we managed well, and this is me in my small car and packing it full with my stuff and yeah, moving away from the Netherlands to Germany. But this is just a side note, and I will briefly explain what I've done in my PhD. So a few goals of my PhD thesis was to extend the list of reversible reactions, which you can apply in protein-templated dynamic combinatorial chemistry, as well as applying it to a number of biological relevant targets, of which today I will talk about one. And we also established the in-house protocol for DCC and published this in a nice review. And a side project which was always running was modeling and docking of molecules for various targets, and also publishing these results in peer-reviewed articles, journals, sorry, I have to say. So as I mentioned in this webinar, I will be talking about an application of a biological relevant target. And for this, the protein-protein interaction is chosen. And you can more or less think of it like this. So you have a protein in red and a protein in yellow, and you would have to find the best combination and key molecule to inhibit or maybe stabilize this protein-protein interaction, so to say, to modulate this protein-protein interaction. And doing this via traditional screening techniques, it's difficult to find lead compounds, so molecules which can fulfill this task. And therefore we thought DCC might be a nice way, an ideal way to find lead compounds which could in the end be turned into real drug molecules. So I will be briefly explaining one of these projects. Sadly enough, I cannot talk about the reversible reactions which have been implemented in DCC. So extending the list of these possible reactions, because it's still not published yet and has some IP problems. And in the end, I will just give a brief conclusion and the outlook of the projects as they are so far. So dynamic combinatorial chemistry, it has been around quite some years already. So it was introduced in the 80s and the 90s. It was introduced in Nature by Hartman and Cuervo, and at the same time also by Lam and Knapp. But the transition to templated DCC followed 10, 20 years later, and this was by Jean-Marie Lane. And basically the templated version of DCC means that you have something which acts as a mold, as a casting or a substrate. So you have something which transitions the reaction, so it helps the reaction to go to a certain of products. And maybe this is still a little bit fake, and therefore I have the next slide available, which makes it a little bit more clearly. So we have a target here in green, and you would use this to template the reaction of possible products. So the best key can fit inside the target. But these keys have to be reversible, so they have to be formed and broken upon time and time again. So for this you need a reaction from building blocks which is reversible, so to say. And for this, dynamic combinatorial chemistry is therefore also dynamic, because you can form these products and have a target amplifying one of its own binders. So then how do you analyze this? So you somehow need to find out which of these molecules are binders, so you can develop into actually drug molecules in the end. But before doing so, I would like to ask you some quick feedback. If you have to design your library, or you have a different library you want to screen, how do you choose your library? So maybe our moderators can open the poll.
I just did this. So do you do like an in situ design of the library, like Alvin mentioned this in the pod, so to say, or do you design them in silico? If you select in silico, we're of course interested in you telling us which tool you're using most likely for this purpose. Or if you let your libraries be designed by the vendor people, and you look in catalogs what they have to offer around your design goals, so to say. So good half of you have voted. I'll give you 5 more seconds and close the poll in 5, 4, 3, 2, 1. So I'm going to share the results here. Alvin, this might be interesting for you. The majority of the people actually does it in silico, even if the people who have told us who they are most of the medicinal chemists. So it's obviously a good interplay going on here between the disciplines. That's a good news. Yeah. And thanks for voting. I will hand back to Alvin then.
Yeah, thanks, Franca, and thanks to all of you for voting. Indeed, also my choice would be in silico, so having a look in maybe co-crystal structures if they are available, to see which kind of interactions you could target. And maybe I will go to the next slide if I have it back here. Yeah, so going back to protein-templated DCC, there are a few factors which are important and which come into play before you can use DCC. So these building blocks, as well as the products, as the solvents, should be biocompatible. So your target, which in our case is mostly a protein or an enzyme, should be happy in these conditions you're screening. So also your building blocks should not be toxic for your target. There's another factor of having pH dependence. So to say that your target protein cannot stand too high pH level, so too basic, or maybe it's favoring an acidic environment. So these are factors you really carefully have to check before you can implement DCC. Then temperature, which is also important. Is your target stable at room temperature, or do you need to cool this? Because at 4 degrees, maybe your reaction is not that fast, but your protein needs this. So there are some important factors which you should keep in consideration. Also, solubility. It's important that your products don't crash out. So for this, you can think of using a co-solvent like DMSO or methanol, if your target allows this, to keep your products as well as your building blocks solubilized. And in the end, also the stability of all components is important. Otherwise, this might drag your reaction in the wrong direction, so to say, that it does not only template by the target, but it crashes out, and therefore you get false positives. So having all of these factors in mind, you have to determine the appropriate buffer. So maybe the buffer has some influence on the reaction, and the next step would then be to prepare your stock solutions, so your building blocks and also the protein, and then determining the ratio, so nucleophile versus electrophile, so the actual reaction which is going on between the building blocks. This is also important, that you have equilibrium, that it can reach equilibrium, or that it can interchange, so that you don't only go to the product side, but it can also go back, so it's really reversible. So how to play around with this? So you have to think about the ratio of these building blocks as well. Then if you have thought about all these important factors, you just add these components together, and then the magic happens. So your target amplifies the reaction, and you would have to analyze this at certain time points. So maybe you can see my mouse. Basically, going through this scheme, there are two ways of analyzing DCC samples. So you have your building blocks, you add a target, so you have a library where your target is added, and then these keys are amplified. They are binding to the target and directing the reaction towards these products, where maybe in a blank reaction, where you don't have the target, you would just reach equilibrium and nothing really changes. So you can compare both of these libraries, and then you would see that there is maybe a difference between them, which is then due to the target. But there is another way of analyzing this. So the first example was the comparative approach, having it compared the both libraries, or you can think of isolating your hit target complex. So filtering out maybe with a gel or a drop down assay or anything you'd like. You can isolate your protein with the complex, the product, and then analyze it via NMR or MS. So you can have these both options, and we normally choose for HPLC-MS, as this nicely separates the products from each other, and combined with the MS you have information which of these peaks having which mass, so you can really say this is my product, and you can compare the blank reaction with the target reaction. So how does this look like? If we compare, for example, now the HPLC chromatograms of a blank library, where you have all the products being formed, with a target library, also having the products being formed, but then there's a change in intensity, also the surface area underneath this peak. So you can compare the surface areas and divide them, and this will give you some template effect. So the ratio between the blank library and the target library. And this gives you information which of these products might be the best binder and therefore could lead to a possible drug candidate. So this is basically the principle behind DCC, and we would apply this in many projects. But what kind of chemistry do you use? Because the reaction we showed you is just an illustration, but we need something real in situ happening. So there was a scheme from my colleague Ramon van der Vlag. He published it with the professor Anna Hirsch in this book chapter 2 years ago, or 3 years already, where they listed reversible reactions which are suitable for DCC. So this might not be for proteins, but in general for DCC which can be reversible. I will not go through all of these the reactions, but the mostly applied reactions which are used are the hydrazone formation. So this one, as well as the acyl hydrazone, having an acyl functionality in there, as well as the imine formation. So these three reactions are mostly applied in DCC. So this is also one of the reactions which I used for these projects, and as mentioned, as one of the goals of the PhD was to extend this list, because this is pretty short and brief, and we want to be able to use different reactions as well, not only being limited to having an acyl hydrazone or only having an imine. So we want to extend it, but sadly enough, I cannot show you this at this stage. Maybe next year I can give an update, but for now, this is it. So coming to the first example, and also the only example for today, is the DCC on the protein-protein interaction. As you might know, protein-protein interactions are being found throughout nature, throughout your body, and they're involved in important processes and also in many diseases. So there was an estimation of existing protein-protein interactions between 130,000 and 650,000 known PPIs. This is quite astonishing, and therefore this is also a relevant target. So we would like to target this PPI and maybe have a handle on curing diseases. So if we can target these interplay of these proteins, this would be really cool. And also in this protein family of the 1433, this is happening. So these PPIs are playing an important role. And just to say a few diseases which you can find it. So for example, Alzheimer's, 1433 is involved in, and also Noonan syndrome and many other diseases. So this 1433 protein family is found throughout the body and throughout many processes. So it's a relevant target, and it's a challenging target. And for the human isoforms, there are 7 known. And I made an overlay of these binding sites in CSAR, and you can see that they are really similar. That's also why they're isoforms. And so if you're going to target one of these isoforms, you might also target another isoform. So how do you get selectivity? And is it not maybe even dangerous to target and try to find inhibitors? So we have thought about this and thought like, yeah, we want to target a certain PPI. So not only the protein itself, but really the complex of the protein interacting with a different protein. And for this, we had a starting point. Of course, we needed to start somewhere, and we looked into literature and found that this nice phosphonic acid compound had a decent affinity towards the 1433, and it was found by Thiel et al. By a virtual screening campaign, and it was a starting point for us to use this into DCC. So we used this compound 1, as I numbered it in here, and thought like, how can we use this and change this to something which is reversible? So we implemented the acylhydrazone linkage. So we thought that it would nicely fit in here. It would more or less keep the same distance between the 2 aromatic rings. And if we keep the phosphonic acid, then we might be having an anchor. So as you can see from this CSAR image, there is some nice hydrogen bond network going on between the phosphonic acid, so the oxygen atoms, and the arginine and the tyrosine amino acids of the protein. So this would really be a good starting point, and then you can use DCC to change the linker, not the linker, the rest of the moiety, and really find molecules which can bind in this pocket. So this is the approach, and we wanted to test first our compound, and we determined the affinity for the protein using SPR. So for those of you who don't know SPR, but I guess most of you do, surface plasmon resonance, it's a technique to determine the binding affinity. In principle, you can have a gold chip where you load your protein or your target of interest in here, and you have a flow channel. Your flow channel contains the target, your ligand, and it can bind to your target, so to your protein. And you will analyze this with light, and when your light beam gets reflected, it might have a different angle. So when it binds, the angle changes, and you would really see when binding occurs. So if you translate this light beam angle shift into this diagram, you can follow the association. And this also gives you kinetics of association. And then afterwards, when dissociation takes place, you can then calculate the affinity of these ligands towards your protein. So this is just in brief SPR, and we use this quite a bit in this project. So first to see if the coating worked, so if our protein was nicely coated on the gold chip and was functional, we used synaptopodin as a ligand to bind to the protein, because this is a known binder of our protein 1433, and it nicely showed us this SPR sensogram. So this textbook example gave us a nice fitting, and it showed that it has decent binding, so good binding, 1.3, 1.4 micromolar, which is pretty good. And our designed inhibitor or modulator had a binding of millimolar. So it's not too well binding, but at least the phosphonic acid, we kept this part, was doing its job. So we thought, okay, we have a basic setting. We know that our protein is active. We know that our main scaffold can bind to the protein, and we have some way of analyzing our hit compounds after applying DCC. So this gave us a nice starting point, and we tried DCC with this phosphonic acid, but with other building blocks as well, having an acid moiety. But then we ran into some problems with not seeing all of these possible products. So that was a bit disappointing, but we continued, and I will show you afterwards. So we wanted to know as well if we have maybe competition, or maybe there is a binding at the same time, so they can even bind and stabilize each other. So the molecule, our designed molecule, can stabilize the complex of synaptopodin with 1433. So for this, we used SPR in a competition assay. We injected our compounds together, so the synaptopodin as our compound in the black line, as well as separately. And in this case, for compound 2, we could see that the addition of having them both injected at the same time was having a bit lower response as the expected calculated addition when you have the blue lines with the red lines combined. So somehow there is some inhibition going, and if there would have been full inhibition, you would expect only the red line or only the blue line. So it's not full inhibition, and it's also not stabilizing, because stabilizing would be completely having the sum of both of these products. So we had some fractional occupancy going on. That means that part of the molecules are binding for the same pocket. So we have some indication that there is inhibition happening with compound 2 towards the complex of 1433 with synaptopodin. And we also proved it in different concentrations. So going to the DCC example, where we applied DCC on the complex of 1433 with synaptopodin, basically it uses the acyl hydroxides as building blocks, as the nucleophile, and aldehydes as the electrophile. And then you would form the combination products as the acyl hydrazones. So you can see it from this scheme. We have our building blocks in here, and our protein would template the reaction, would favor maybe one or two of these possible products, and hopefully we can then analyze this and see which of these compounds are hits. So as I mentioned at the beginning, you would like to see which are templating or templated by the protein, and for this you need the protein in one of the reaction mixtures, and maybe a blank reaction where you don't have the target, don't have the protein target. And in this case, we wanted a third reaction, so to say the complex, and therefore we used the 1433 with synaptopodin. So going to the real chromatograms, on top there is the blank reaction, where we could observe all the products, and basically here are two products which are having amplification when the protein is added. So in this second chromatogram, this is with the protein, and in the third chromatogram we have the protein synaptopodin complex. So these are more or less the same, meaning that the compounds are stabilizing. So if these compounds would have been amplified by the protein, but not in presence of the synaptopodin, then we would have had inhibition, and these peaks would have been lower. So by having them in the same height and having the same surface area, we have a hint that these compounds might stabilize the complex of the protein with our other protein, so the synaptopodin with 1433. This is a nice finding, and this was novel and new. And we wanted to make sure that these compounds were indeed the ones which we think they were. So from the mass, we knew that it should match with A1H3, and the second would be H2H3. So we synthesized these compounds and then run the HPLC MS again, and could see that it's indeed the compounds we were thinking they would be. So we have these compounds in hand, so these hit compounds, pure after synthesis, and we wanted to test them with SPR as well, as mentioned in the beginning of this example. So these both compounds were showing not too great affinity. I have to say that these SPR sensograms are not too great, but at least we can use them and see that there are some binding events going on, and we calculated and evaluated the affinity, and it was found that they are around 16-15 micromolar for these both hit compounds. So the next step would then to be the competition assay to see if we now have this inhibition, or maybe, as was expected from the DCC results, that it would have stabilizing effect. So for this, we used again the addition of the synaptopodin with the compound, and separately synaptopodin and the compound also separately. And as you can see from this diagram, from this sensogram, I should say, is that there is some additive effect. So the red line, being synaptopodin, has a lower response unit than the combination. So somehow our compound is influencing the complex. It's having a positive effect. And this is as well the case for the other compound. Maybe a little bit minor effect than this. Maybe there are some problems with the response, but at least it shows that there is an additive effect, and this would indicate as well from the DCC observation that it would stabilize. And this is a new finding for DCC, and a nice application where we could show the utility of and the use of DCC in these kinds of projects. Sadly enough, I cannot show you the structures. It would be nice, and we have submitted the research in medchem letters, ACS, and it's now under review, and I would have hoped it to be accepted by now, and I could have shown you it, but sadly enough, I cannot show you it today. And this is already the conclusion slide for this project, and we used DCC as a first application on a PPI. So this is some new way of finding modulators of protein-protein interactions. We used SPR to analyze these hit compounds. We also used fluorescence polarization assay, and also microscale thermophorese. But these are less likely, or to say, how to rephrase, not too great techniques compared to SPR. SPR is using less compound and less protein, and we prefer this over handling compared to the other techniques. Then two of these hit molecules were found to be stabilizers of this particular complex, and as an outlook, the status of these projects is that they are now being tried to crystallize these molecules with 1433, and also afterwards, if this succeeds, then we can apply a structure-based drug design approach in a second round with DCC and finding optimized compounds for these complexes. So basically this is already it. Yeah, sadly enough, I cannot show you the other work I've done, but there are a few people I would like to thank. So Justin and Franca, who are hosting now this webinar, and as well Dr. Marcus Gastreich and Dr. Christian Lemon for being colleagues here at Biosolve. and a few professors which have been my mentors, Professor Anna Hirsch, Professor Adriaan Minnaert, and Professor Rolf Müller. So a big thanks to these amazing persons and mentors to me. And for the 1453 project in Saarbrücken, I would like to thank Dr. Walid Elgaher, the student which was helping a lot in the synthesis and in the project, Nathalie Hedrich, and of course Anna for guidance. And from Eindhoven, the collaborators, Dr. Sebastian Andrei and Professor Dr. Christian Ottman.